Everyone talks about chaos like they understand it, entropy, disorder, the universe falling apart. But there was one man in Vienna who saw something nobody else saw. Not just what chaos is, but why it happens. Why you can scramble an egg but never unscramble it. Why time moves forward and never back. Ludwig Boltzmann figured it out in 1872 with a single assumption that broke physics. An assumption so simple it sounds obvious until you realize it destroys the symmetry of every equation Newton ever wrote. Who was this man? What did he see? And why did the physics world spend 30 years trying to prove him wrong? Boltzmann understood chaos as probability, not randomness, not mess, probability, and that changed everything. November 2004 and continuously updated, and from peer-reviewed papers in the European Physical Journal H from 2021 on Boltzmann's reply to Loschmidt, specifically Olivier Derigal's commented translation examining Boltzmann's original 1877 response. These are deep, archival sources that preserve the actual mathematical arguments and correspondence between Boltzmann, Loschmidt, Ostwald, and Mach. Now back to the information. In 1866, Boltzmann completes his doctorate on kinetic theory of gases at age 22. Stefan introduces him to James Clerk Maxwell's work from 1867. Maxwell had used statistics to describe gas molecules. Temperature was molecular speed, pressure was collision. Boltzmann sees something Maxwell missed. A bridge between Newton's clockwork universe and the thermal chaos everyone measures in laboratories. At 25, in 1869, Boltzmann becomes full professor of mathematical physics at the University of Graz, the youngest chairholder. He has already connected thermodynamics to probability, but the connection is fragile, incomplete. Never the reverse. Gases expand into empty space, never compress spontaneously. The universe tends toward disorder. Everyone accepts this. The problem is mechanism. How does it happen? Clausius gave description, not explanation. Boltzmann wants the why. Further studies on the thermal equilibrium of gas molecules. In this paper, he introduces what will be called the H theorem. The H is a function that measures deviation from equilibrium. Boltzmann proves H can only decrease over time. Decreasing H means increasing entropy. The gas moves toward uniformity, disorder, maximum probability. He derives this from one assumption, molecular chaos, the Stossal-Ansatz. It says particle velocities before collision are uncorrelated, independent, random. After particles collide, before they collide again with other particles, the assumption says their velocities are still uncorrelated with the velocities of other particles. This seems reasonable. There are so many particles. 10 to the 23rd molecules in 1 cubic centimeter of gas at room temperature and pressure. Surely they bounce around randomly. Surely correlations wash out. If you reverse time, those velocities would still need to become uncorrelated. But reversing the equations would create correlations instead. Molecular chaos picks a direction. It chooses the arrow of time. Without ever admitting it is a choice. The physics community reads the paper. Most ignore it. A few understand what he attempted. One man sees the flaw immediately. Joseph Loschmidt, Boltzmann's former teacher, now colleague at Vienna, lifelong friend. Loschmidt has no issue with atoms. He calculated atomic sizes himself. But he sees the logical trap. In 1876, Loschmidt publishes Über den Zustand des Wärmegleichgewichtes eines Systems von Körpern mit Rücksicht auf die Schwerkraft. On the state of thermal equilibrium of a system of bodies with consideration of gravity. The title hides the attack. In the text, Loschmidt presents what becomes known as the reversibility paradox. Now at some later time, say 5 minutes, reverse every velocity. Every particle that was moving right now moves left. Every upward momentum flips downward. The laws of motion are time symmetric. This reverse state is a valid solution to Newton's equations. What happens? The particles retrace their paths backward. At 10 minutes, they return to the corner. Entropy has decreased. H has increased. The second law is violated, not forbidden. Just violated. The theorem cannot be universal. There must be initial conditions where entropy decreases, and if there are any such conditions, why do we never see them? Satz ist zum zweiten Hauptsatz der Wärmetheorie. On the relation of a general mechanical theorem to the second law of thermodynamics. This response changes everything. Boltzmann admits Loschmidt is right. There are initial states where entropy decreases, but these states are fantastically improbable. Not impossible. Improbable. The universe does not forbid them. Statistics crushes them. There are overwhelmingly more ways for molecules to be disordered than ordered. Think of it this way. One corner configuration, one specific arrangement with all molecules clustered. But spreading throughout the box, countless arrangements, uncountable configurations. The ratio is astronomical. If you have 100 molecules and 100 cells, the number of ways to put all molecules in one cell is 1. The number of ways to distribute them across all cells approaches 10 to the 157. The probability of the ordered state is 1 divided by that number. Effectively 0, not absolutely 0, effectively 0. It is statistical, probable, overwhelmingly probable but not guaranteed. The universe could reverse, eggs could unscramble, heat could flow cold to hot. The chances are so small that you would wait longer than the age of the universe, trillions upon trillions of times longer, but possible. This is the shift, from determinism to statistics, from must to almost certainly. 1877 is the year Boltzmann publishes his second great paper that year, über die Beziehung zwischen dem zweiten Hauptsatz der mechanischen Wärmetheorie und der Wahrscheinlichkeitsrechnung, respektive den Sätzen über das Wärmegleichgewicht, on the relationship between the second law of thermodynamics and probability calculus with respect to the theorems about thermal equilibrium. This is the combinatorial paper, the one that defines entropy in terms of microstates. A macrostate is what you measure: temperature, pressure, volume, energy. A microstate is one specific arrangement of all particle positions and velocities that produces that macrostate. There are many microstates for each macrostate. The number of microstates is W. Boltzmann defines entropy as proportional to the logarithm of W. Why logarithm? 2 reasons. First, entropy is additive. If you combine 2 systems, total entropy is the sum. But the number of combined microstates is the product. The logarithm turns products into sums. Second, logarithm compresses the scale. W can be 10 to the trillion. The logarithm keeps the numbers manageable. This formula was later refined by Max Planck in 1900, who added the constant K, now called Boltzmann's constant. K equals 1.38 times 10 to the minus 23 joules per Kelvin. The formula reads S equals K times natural log of W. This is the equation on his tombstone. A gas at room temperature has 10 to the insane power microstates, high entropy. The second law becomes a statement about where systems go, from rare configurations to common configurations, from unlikely to likely, from special to generic. Always. Because there are more ways to be generic than special. The universe does not prefer disorder. Disorder does not attract systems. The universe is indifferent. But disorder is the overwhelming majority. Roll the dice enough times and you land on the majority. Always. Therefore, atoms are convenient fictions, mathematical tools. Boltzmann defends atoms, not as absolute reality, as useful pictures, models, analogies. He says science needs hypotheses. You cannot do physics without proposing mechanisms. The fruitfulness of atomism proves its value. Mosch and Boltzmann clash constantly, not violently, not personally hostile at first, but philosophically opposed. Boltzmann finds the atmosphere suffocating. The disagreements grind on him. In 1894, Boltzmann moves back to Vienna to the chair of theoretical physics when Stefan dies. The next year, Mach takes the philosophy chair. Boltzmann hates it. In 1900, he leaves Vienna for Leipzig specifically to escape Mach. Irony, in Leipzig, he becomes colleague of Wilhelm Ostwald, his strongest scientific opponent. Founder of physical chemistry? But Ostwald champions energetics. Energetics says energy, not matter, is fundamental. All physical processes reduce to energy transformations. No need for atoms, no need for molecules. Just energy in various forms: heat, kinetic, potential, chemical. This is the 19th century version of energy monism. Ostwald develops this into a full program. He writes textbooks, founds journals, gathers followers. He believes energetics will unify all science. Mechanics, thermodynamics, chemistry, biology, all under energy. Boltzmann thinks this is wrong. Not just wrong, backwards. Energy without atoms is empty formalism. No mechanism, no explanation, just redescription. The meeting is programmed to feature energetics. Boltzmann is on the organizing committee. He suggests they invite Georg Helm from Dresden to present energetics. Helm is Ostwald's ally, smart physicist, clear thinker. Boltzmann also suggests inviting Ostwald to speak. The organizers agree. Manuscripts circulate beforehand. British style, open discussion. Everyone expects civil academic exchange. Boltzmann has other plans. At the meeting, Boltzmann attacks, devastatingly. He dissects energetics point by point, shows it cannot derive equations of motion, cannot specify microstates, cannot explain irreversibility. It is taxonomy, Boltzmann says, classifying energies, not explaining processes. Helm presents his paper. Boltzmann tears it apart. Ostwald defends energetics. Boltzmann crushes the defense. Felix Klein backs Boltzmann from the mathematics side. Max Planck, though not present at Lübeck, later publishes papers supporting Boltzmann and attacking energetics. Arnold Sommerfeld, a young mathematician attending the meeting, later writes his impression. The fight between Boltzmann and Ostwald resembled the struggle between a bull and a supple fighter. But the bull defeated the matador in spite of all the fencing skill. The arguments of Boltzmann broke through. We, the young mathematicians of that time, were all on the side of Boltzmann. Ostwald finally abandons energetics in 1908 after Jean Perrin's experiments on Brownian motion confirm Einstein's 1905 calculations based on atomic theory. Too late for Boltzmann. He never sees vindication. Based on Henri Poincaré's recurrence theorem from 1890, Poincaré proved that any bounded mechanical system with fixed energy returns arbitrarily close to its initial state if you wait long enough. Recurrence is guaranteed, not if, when. The recurrence time can be enormous, longer than the age of the universe, but finite. Zermelo applies this to gases. If Poincaré is right, then any gas eventually returns to low entropy. Disorder eventually becomes order again. The second law is not even statistically true. It is periodically violated. Boltzmann responds. He says yes, recurrence happens, in principle. But the recurrence time for macroscopic systems is unimaginably long. For a box of gas with 10 to the 23 particles, the Poincaré recurrence time is roughly 10 to the power 10 to the 23 seconds. The age of the universe is about 10 to the 17 seconds. The recurrence time dwarfs cosmic history by factors that make infinity look close. We will never see it. Ever. Statistical mechanics applies to the timescales we observe, not to abstract eternity. The second law holds for all practical purposes. Zermelo is technically correct. Boltzmann is practically correct. Science deals with the practical. Boltzmann battles Mach on philosophy, Ostwald on energetics, Zermelo on recurrence. Others criticize molecular chaos, others question statistical interpretation. Every paper Boltzmann publishes gets scrutinized, challenged, misunderstood. He writes in his preface to the lectures on gas theory in 1896, "I am conscious of being only an individual struggling weakly against the stream of time. But it still remains in my power to contribute in such a way that when the theory of gases is again revived, not too much will have to be rediscovered." He knows he is ahead, he knows he is right, but he feels the isolation, the rejection, the constant need to defend what should be obvious. He dictates manuscripts, he suffers asthma attacks at night, headaches from overwork, possibly angina pectoris, heart issues. His health crumbles. Mentally, he struggles with mood swings, severe depression alternating with manic productivity. He jokingly attributes this to being born between Mardi Gras and Ash Wednesday. Feast and fast, joy and ash. But it is not a joke, what we would now diagnose as bipolar disorder. He attempts suicide multiple times during his life, once during his time in Leipzig. The depression deepens, the isolation increases. In 1901, Mach retires from Vienna due to illness. Boltzmann's reason for leaving Vienna disappears. In 1902, Boltzmann returns to Vienna to reclaim his chair of theoretical physics. The university also assigns him Mach's philosophy course. Boltzmann's philosophy lectures become wildly popular. The biggest lecture hall overflows, students crowd the aisles. Boltzmann teaches natural philosophy, realism versus idealism, scientific method, probability, evolution. He admires Darwin, considers evolution the greatest discovery of the 19th century. He connects evolution to thermodynamics, order from disorder through selection. Entropy locally decreases where energy flows. Life is a low entropy state maintained by energy input. The sun, food, the lectures bring temporary happiness, recognition. But underneath, the depression never leaves. Boltzmann is forced to resign. 4 months later, September 5th, 1906, Boltzmann is on vacation with his wife, Henriette, and their youngest daughter in Duino, a coastal town near Trieste, then part of Austria, now Italy. While his wife and daughter swim in the bay, Boltzmann hangs himself in their room. No note, no explanation. He is 62 years old. His daughter discovers the body. The tragedy is timing. Within 2 years, Jean Perrin's experiments on Brownian motion vindicate atomic theory completely. In 1908, Perrin measures Avogadro's number using Einstein's 1905 theory of Brownian motion. The measurements confirm Boltzmann's constant, confirm the statistical interpretation, confirm everything Boltzmann fought for. Wilhelm Ostwald recants energetics that same year, admits atoms are real. Ernst Mach never fully concedes, but his influence wanes. By 1910, atomism wins. Statistical mechanics becomes foundational. Quantum mechanics emerges from it. Max Planck uses Boltzmann's statistical methods to solve black body radiation in 1900, quantizes energy, launches quantum theory. Einstein uses Boltzmann's statistics throughout his work. 1905 miracle year, Brownian motion, photoelectric effect. Special relativity, all touch Boltzmann's ideas. 1907, Einstein writes, Boltzmann's work on thermodynamics will never lose its importance. Gibbs in America independently develops similar statistical mechanics. Their approaches merge, the field explodes. Information theory in 1948. Claude Shannon defines information entropy using the same logarithmic structure. The connection between thermodynamic entropy and information entropy becomes fundamental. Ludwig Boltzmann's equation, S equals K log W, etched on his grave in Vienna's Central Cemetery. Zentral Friedhof. Section 14, Group 6, grave number 38. The tombstone bears his bust. The formula below, no dates, no epitaph, just the equation. And this is perfect, because the equation contains everything, his genius, his struggle, his vision of reality. Chaos is not mess. Chaos is multiplicity. The more ways something can happen, the more likely it is. The second law is not a law about nature preferring disorder. The second law is a law about combinatorics, about counting. There are more ways to be chaotic than ordered. That is all. That is everything. But large systems with many particles behave statistically. The probability of moving from low entropy to high entropy is near certainty. The probability of moving from high entropy to low entropy is near zero. Not forbidden, just crushingly unlikely. Time flows forward because forward means toward probable states, toward majority states. The arrow of time is the arrow of probability, not carved into fundamental laws, carved into numbers, into statistics, into the overwhelming weight of multiplicity. The H theorem works only forward, not backward. The asymmetry is not in the collisions. The asymmetry is in the assumption about correlations. Boltzmann does not fully admit this in 1872. He comes to understand it through Loschmidt in later debates. By the 1890s, he knows the irreversibility of thermodynamics comes from assuming a special initial condition. The universe started in a low entropy state. Why? Nobody knows. But given that it did, and given molecular chaos, entropy must increase. The second law is not fundamental. It is conditional, contingent on cosmic initial conditions. This is brilliant and disturbing. With 10 to the 23rd particles, you cannot track individual trajectories. You must think in distributions, in ensembles, in statistical spaces, not what will happen, what will probably happen, not trajectories, probability clouds. This is pre-quantum mechanics. Quantum mechanics would make probability fundamental in 1926. Boltzmann made it fundamental in 1877 for different reasons. But the mathematical structure is similar. The conceptual leap is enormous. His colleagues trained in classical mechanics could not make it. They wanted certainty, determinism. Boltzmann offered overwhelming likelihood, good enough for any practical purpose, but not absolute. The physics community wanted absolutes. Boltzmann gave them statistics. Kinetic theory connects particle motion to thermodynamic properties. Temperature is average kinetic energy. Pressure is momentum transfer from collisions. These connections were known. Maxwell established them. Boltzmann went further. He connected entropy, the most abstract thermodynamic quantity, to microscopic counting. S equals K log W makes entropy a bridge. On one side, the macroscopic world. Heat, work, engines, efficiency. On the other side, the microscopic world. Atoms, molecules, probabilities, configurations. The formula links them, not approximately, exactly, up to the constant K. This bridge made statistical mechanics possible. This bridge made quantum statistics possible. This bridge made information theory possible. Shannon's entropy formula in 1948. H equals negative sum of P times log P, same structure. Information is microscopic configurations. Uncertainty is macroscopic ignorance. The logarithm links them. Boltzmann saw this pattern in 1877. Shannon rediscovered it in 1948. The structure is universal, deeper than thermodynamics, deeper than physics. A statement about how complexity emerges from simplicity through counting. Maximum likelihood. The equilibrium distribution of a gas is the Maxwell-Boltzmann distribution. Why? Because it is the most probable distribution, the one with the most microstates. When a gas reaches equilibrium, it has explored phase space, sampled configurations, settled into the region with the highest statistical weight. Equilibrium is not a special state. It is the generic state, the boring state. The state you land on if you shuffle randomly. Boltzmann showed this mathematically, derived the Maxwell-Boltzmann distribution from counting, from combinatorics, from pure probability assuming equal likelihood of microstates. No dynamics needed, just statistics. This is profound. Thermodynamic equilibrium, which experimentalists measure and engineers use, reduces to a statement about probability. The system is in equilibrium because it is in the most probable state. Done. Brownian motion shows this. A pollen grain jiggling in water sometimes moves against the average. Entropy locally decreases. Violating the second law briefly. This is real. Observable. Boltzmann predicts it. The fluctuation-dissipation theorem in 20th century physics quantifies it. Relates fluctuations to dissipation. Microscopic reversibility to macroscopic irreversibility, all traceable to Boltzmann's insight. The second law is statistical. Statistics has fluctuations. Large deviations theory, developed in 20th century mathematics, formalizes Boltzmann's 1877 discovery. The probability of large deviations decays exponentially with system size. For macroscopic systems, deviations are negligible. For microscopic systems, deviations are significant. Boltzmann understood this distinction. His critics did not. He understood that science is about models, not ultimate reality. Boltzmann debates Mach on this. Mach wants science free of metaphysics, observable only. Boltzmann agrees science should stick to observables, but he argues you need models to connect observations. Atoms are a model, a picture, a mechanical analogy, useful for organizing data, predicting experiments, calculating properties. Boltzmann never claims atoms are the final truth. He claims atoms are the best current model, fruitful, productive, elegant. In his philosophy lectures and writings, Boltzmann defends pluralism, multiple models, different pictures for different domains, mechanical models for gases, field models for electromagnetism, statistical models for thermodynamics. The choice depends on fruitfulness, not metaphysical commitment. This is sophisticated philosophy of science. Anticipates 20th century model-based reasoning. Boltzmann, the physicist, is also Boltzmann, the philosopher, deeply thoughtful about scientific method, about the limits of knowledge, about the role of mathematics in describing nature. His philosophical writings deserve more attention. They show a mind grappling with foundational issues, not dogmatic, open, critical, humble despite brilliance. Statistical mechanics becomes one of the three pillars of modern physics. Classical mechanics, electromagnetism, statistical mechanics. Quantum mechanics builds on statistical mechanics. Quantum states are microstates. Quantum entropy is Boltzmann entropy for quantum systems. Boltzmann statistics become Bose-Einstein statistics or Fermi-Dirac statistics, depending on particle type. But the structure remains. Logarithm, counting, probability. Information theory emerges from statistical mechanics. Shannon cites Boltzmann. The bit, the unit of information, connected to thermodynamic entropy through Landauer's principle in 1961. Erasing one bit costs at least kT-ln2 joules. Information is physical. Thermodynamics constrains computation, all from Boltzmann's formula. Complexity science uses entropy. Chaos theory uses entropy. Network theory, machine learning. Artificial intelligence, all use entropy measures. All descendants of Boltzmann's insight. Entropy as counting, entropy as uncertainty, entropy as information. The concept propagates through science, unifying disparate fields, providing common language, common mathematics, common intuition. After Boltzmann, physics includes statistical ensembles, probable outcomes, average behaviors. This shift enables modern physics. Quantum mechanics is fundamentally statistical. Einstein resists. God does not play dice, but quantum mechanics wins, and the statistical thinking comes from Boltzmann, not the randomness. Quantum randomness is different, but the probabilistic framework, the ensemble thinking. The acceptance that fundamental theories can give probabilities, not certainties. Boltzmann pioneered this. Thermodynamics was the first place it appeared. Quantum mechanics generalized it. Now it is everywhere. Risk analysis, climate models, epidemiology, economics, all use statistical thinking. All trace lineage to Boltzmann's revolution. Not credited often, but there. He dies in 1906, thinking his work will be forgotten. He writes in his final years of being a lone voice, a powerless individual against the currents of time. He is wrong, but he does not know he is wrong. 2 years after his death, the atomic theory controversy ends. Atoms win. Statistical mechanics becomes mainstream. Students learn Boltzmann distributions, Boltzmann constants, Boltzmann equations. His name becomes synonymous with statistical physics. But he is not there to see it. He does not see Planck credit him. He does not see Einstein build on his foundation. He does not see quantum mechanics emerge. He does not see information theory connect to thermodynamics. He does not see his equation carved into marble and placed on his grave as physics tribute. A quiet Austrian physicist, fighting for ideas nobody understood. battling colleagues who rejected his vision, struggling with depression and isolation, dying just before vindication. The story is almost Greek tragedy, except the ideas survive, flourish, transform science, and that is enough. 5 symbols, a universe of meaning. The chaos you see is probability, the entropy you measure is microstates, the arrow of time you experience is statistics. Ludwig Boltzmann understood this in 1872, published it in 1877, defended it for 30 years, died without recognition. 2 years later, physics agreed. The equation remains, the man is gone. But the understanding persists, carved in stone. Printed in textbooks, taught in classrooms, applied in laboratories. Chaos is not disorder. Chaos is probability. And probability is counting, the way Ludwig Boltzmann counted better than anyone before or since. Hypothesis. All things are made of atoms. Feynman credits this to the importance of atomism, but the full content of that statement includes Boltzmann's statistics, atoms in motion, colliding, creating temperature, creating pressure, creating entropy through probability. The atomic hypothesis needs Boltzmann's insight to have content, to connect to thermodynamics, to explain why we see what we see. Feynman knows this. He teaches statistical mechanics. He uses Boltzmann's equation. The historical connection sometimes gets lost. Students learn the formula, memorize it, apply it, but miss the revolutionary nature, the struggle, the genius, the way one man saw deeper than his entire generation into the nature of chaos, into the nature of probability, into the nature of time itself, and paid for that vision with isolation, depression, and death just before victory. The mathematics behind Boltzmann's understanding deserves deeper examination. When he wrote down the H function in 1872, he defined it as the integral of f times log f over velocity space. Here, f is the distribution function, the number density of particles with velocity v at position r and time t. The H theorem states that dh divided by dt is less than or equal to 0. H decreases, always, or stays constant at equilibrium. To prove this, Boltzmann considers binary collisions. 2 particles with velocities v1 and v2 collide. After collision, they have velocities v1 prime and v2 prime. Conservation of momentum and energy constrain the possible outcomes, but many collision angles satisfy the constraints. Boltzmann averages over these angles. He then invokes molecular chaos. The number of collisions between particles with velocities v1 and v2 is proportional to f of v1 times f of v2, not some correlated function. This factorization is the key. It allows him to write the collision integral, the term describing how collisions change the distribution. With molecular chaos, he can show the collision integral makes h decrease. Without molecular chaos, the calculation fails, the proof collapses. This is why molecular chaos is essential, not peripheral, essential. The entire edifice of the H theorem rests on it. Most cluster around the average. The average kinetic energy equals 3/2 kT. Temperature is motion. This distribution maximizes entropy, subject to fixed energy and particle number. It has the most microstates, the highest statistical weight. Any other distribution has lower entropy. Higher H will evolve toward Maxwell-Boltzmann through collisions. This is equilibration, the approach to equilibrium. Boltzmann quantified it, gave it mathematics, made it predictive. How many ways can n particles distribute among these cells with total energy E? This is combinatorics, permutations and combinations. The answer is a multinomial coefficient, huge number, grows exponentially with n. Boltzmann takes the logarithm, defines entropy as proportional to this logarithm. He shows this definition agrees with thermodynamic entropy up to an additive constant. The constant does not matter for entropy differences. Only differences are measurable in thermodynamics. Absolute entropy requires quantum mechanics and the third law, but Boltzmann gets the structure right. S equals k log W. The proportionality constant k connects the two worlds, microscopic and macroscopic, statistical and thermodynamic. Fine for calculations, but what is it? What does it mean? Boltzmann answers, entropy measures the logarithm of accessible states, physical, concrete, countable in principle, not countable in practice. 10 to the 23rd particles means 10 to the 10 to the 23rd states. Uncountable, but conceptually clear. This clarity is what Boltzmann provides. He makes entropy intuitive. Well, as intuitive as logarithms of enormous numbers can be. If you value documented physics history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Boltzmann provides the theoretical proof in 1884. He uses thermodynamics and Maxwell's electromagnetic theory. The derivation is elegant, considers a cavity filled with radiation in thermal equilibrium. The radiation exerts pressure on the walls. Pressure is energy density divided by 3 for electromagnetic radiation. Using thermodynamic relations and Maxwell's equations, Boltzmann derives the T to the 4th law. This becomes the Stefan-Boltzmann law. Constant sigma equals 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the 4th. Critical for astrophysics, stars radiate according to this law. Luminosity depends on surface area and 4th power of temperature. Giants are cool but huge. Dwarfs are hot but tiny. The law governs stellar energy output. Boltzmann proved it from fundamentals. Stefan measured it. Both names honored. This is 19 years before Planck's quantum black body solution. Boltzmann's derivation is classical, correct in the limit. Planck's quantum derivation fixes the ultraviolet catastrophe and gives the full spectrum. But the T to the 4th law survives, valid quantum mechanically. Boltzmann's contribution stands. Each degree of freedom in a system at temperature T has average energy 1/2 kT. Translational kinetic energy has 3 degrees of freedom, 3 directions. Total average kinetic energy is 3/2 kT per particle. Rotational energy adds more. Vibrational energy adds more. Boltzmann establishes this using his statistical methods. It works classically. Breaks down quantum mechanically at low temperatures, where degrees of freedom freeze out. But at high temperatures, quantum approaches classical. Equipartition holds. Boltzmann derives it from first principles, from the canonical ensemble, from Boltzmann statistics. Again, the framework he builds enables later developments. He publishes elementary principles in statistical mechanics in 1902. Gibbs introduces ensembles systematically. Microcanonical, canonical, grand canonical. He defines the Gibbs entropy. S equals minus k sum over all microstates of p times log p. Here, p is the probability of each microstate. For equal probabilities, p equals 1 over w. The Gibbs entropy becomes k log w. Boltzmann's formula. The two approaches merge. Boltzmann focuses on isolated systems with fixed energy. Microcanonical, Gibbs generalizes to systems in contact with heat baths. Canonical, or particle reservoirs, grand canonical. The formalism Gibbs develops becomes standard, but the physical insight is Boltzmann's. The connection to thermodynamics, the statistical interpretation of entropy. Gibbs provides mathematical machinery. Boltzmann provides physical understanding, both necessary. Both brilliant. Gibbs never meets Boltzmann. They correspond minimally, but they create the same theory from different angles. Independent discovery, common in science when ideas are ripe. The time was right for statistical mechanics. Both men had the genius to see it. His lectures on natural philosophy, published as Populäre Schriften in 1897, contain essays on scientific method, on the nature of models, on evolution and thermodynamics, on determinism and probability. He defends mechanical pictures, rejects pure phenomenalism, argues science needs hypotheses to progress. But he also emphasizes the provisional nature of scientific theories. We build models, test them, revise them, discard them if better models appear. Atomism is his best model, not final truth, best current hypothesis. This humility contrasts with his public persona. Boltzmann in debate is fierce, uncompromising, attacking weak arguments, demolishing opponents. But Boltzmann in writing reveals uncertainty, self-doubt, awareness of limits. He knows he does not have final answers. He has better answers than alternatives. That is enough for science. For him, apparently not enough for peace. Searching for acceptance, searching for understanding, searching for colleagues who see what he sees. He never fully finds it, not in life, but physics remembers. The equation remains, the insights remain, the legacy remains. Ludwig Boltzmann, born February 20th, 1844, died September 5th, 1906. The man who understood chaos better than his generation could imagine, the man who saw probability in disorder, statistics in entropy, multiplicity in chaos, the man whose equation explains why you can scramble an egg but never unscramble it, why time flows forward, why the universe tends toward high entropy states, not because it must, because it probably will. And probability over cosmic timescales with cosmic numbers of particles becomes practical certainty. That is genius. That is Boltzmann.